everybody. Today I am going to start with this example, but this example is actually the example related to the infinite expansion of Taylor series. What is infinite Taylor series? We all know that the Taylor series may be in H theta form or in Maclaurie's form. We already have proved a Taylor series earlier. The equations of the Taylor's theorem says that if a function f in minus 1 is continuous in the closed interval, and if this nth derivative exists in the open interval, and p is a positive integer, then there exists a number theta where 0 less than theta less than 1, such that the function f of a plus h can be written in this way. And this Rn was the remainder after n terms, and it has three different expressions as I proved in our previous classes, in generalized form of remainder, in Lagrange's form of remainder, and in Cauchy's form of remainder. Actually, if you consider all these expressions, the numerical value of Rn remains same. Just this quantity theta, the value of theta, which is a number in between 0 and 1, the theta is adjusted in such a manner that this numerical value of the remainder Rn remains same. However, for generalized form of remainder, we get this first expression. For generalized form of remainder, we get this first expression. Then for Lagrange's form of remainder, we get this second expression, and for Cauchy's form of remainder, we get this third expression. So that is all about the change in the value of theta. Okay. Although the remainder Rn, the numerical value of the remainder would not change after remainder after n terms. Now we want to find whether this expansion can be expanded up to infinite terms. And if it is expanded up to infinite terms, then obviously this quantity, this Rn, this remainder Rn should tend to 0, isn't it? This remainder Rn should tend to 0 as n tends to infinity. Okay, so it is clear that for Taylor's infinite series, the remainder Rn must tend to 0 as n tends to infinity, of course. And in that case, we need few more other conditions. What are the conditions? The conditions is that these quantities, these f n minus 1, it should also be continuous in the closed interval for sufficiently for, you can say, not sufficiently large n, rather for all large and larger n, this f n minus 1 must be continuous. And of course, in that if it is continuous, then the lower order derivatives should exist, and they must be continuous. What I mean to say is that all the function f should be infinitely differentiable, and all the derivatives of that function must be continuous in this kind of closed interval. Then only we can extend this expansion up to infinite number of terms, because in successive terms, this is in this nth term we have f n minus 1, n minus first derivative of f. Similarly, in the next term we shall have nth derivative, and after that we shall have n plus first order derivative. So all these derivatives must exist on the closed interval, and it must be continuous there. Then only we can have Taylor's infinite series expansion. Okay, so that's all about the Taylor's infinite series expansion. the detailed computation is not included in your syllabus. What is included in your syllabus is the application of this Taylor's infinite series for particular few standard functions. Okay, so let me go to the those functions what I was trying to prove. For example, first of all, we have the function over here e to the power of x. Yeah, this one. First of all, we have the function e to the power of x, and this was a question that was selected in the university examinations few years back. I'm just writing the question in toto. It says that find the power series expansion of e to the power of x, stating clearly its region of validity. That means in this kind of expansions, we need to check we need to check the range of x at which the infinite series expansion would be valid. Sometimes in this kind of problems, the infinite series expansion remains valid for all values of x. If it is valid for all values of x, then we should say that the function infinite series expansion of the function is valid for x varying from minus infinity to plus infinity. But in some cases, the expansion is not valid for all values of x. Okay. So I am going to discuss a few more examples after this one, and in this discussion, it would be clear that some of the functions are there for which the infinite series expansion is valid for all values of x. However, some functions are there for which the infinite series expansion is valid only to some restricted interval of x. Okay, so let's start the lecture by considering this function e to the power of x. This e to the power of x is a function. We know that the derivative of e to the power of x, this nth derivative of e to the power of x is equal to the same function e to the power of x for all value of x belonging to the real number system R, and for all integer n. It is true for all integer n. And so we can say that the function is infinitely differentiable, and all these derivatives are continuous there in each and every interval. And remember, over here we shall always try to consider this interval 0 comma x. We shall try to apply the Maclaurin series expansion. Got it? So our target would always be to consider this kind of interval 0 comma x. Anyway, now over here over here for the simplicity we are considering the Lagrange's form of remainder, but sometimes in other cases, whenever the expression of Lagrange's form of remainder would not give us the required result is actually what is this. Our target is to show that this remainder Rn should tend to 0. Got it? As n tends to infinity. So our target is to show that this remainder Rn is tending to 0 as n tending to infinity. And sometimes the Lagrange's form of remainder, which is actually the most simplest form of remainder after n terms, sometimes we use Lagrange's form of remainder. However, in many cases it is found that the Lagrange's form of remainder is not much suitable or not much handy to prove the fact that Rn tends to 0 as n tends to infinity. And in those cases, what we do, we then consider the Cauchy's form of remainder or the generalized form of remainder, other expressions of the remainder. Mostly the Cauchy's form of remainder would give us the required result. So for the starting, we are considering this Rn in the Lagrange's form of remainder. Got it? So over here we know that nth derivative of x is equal to fn x, that is actually our e to the power of x. So just by putting x is equal to theta x in equation number 2, we got the expression of nth derivative fn at the point theta x. Now we have a result in the chapter of sequence. What is the result? Related to the null sequence. What is the result? The result says that if we have a sequence uh, like this kind of sequence an, an, then this an is tending to 0. We can prove that this an is tending to 0 if this expression, if this modulus of an plus 1 divided by an with n tending to infinity, if this quantity is less than 1. Okay, if this quantity is less than 1, then we can prove that this sequence an tends to 0 as n tends to infinity. So it is about null sequence, this kind of sequence which are tending to 0 as n tending to infinity. This kind of sequences are called null sequences. So we shall mostly try to use this result over here. And in order to prove this result, we shall apply the sandwich theorem for sequence. Anyway, how to apply this one? Let's see. We already have the inequality that 0 less than theta less than 1. And for the sake of simplicity, at first we consider that x is greater than 0. Over here we are taking the fact that x is greater than 0, and the same kind of inequality can be established if x is less than 0. Let's see how can we prove this result. Over here we are multiplying this inequality by x. Then what we shall have? We shall have this type of result: 0 less than theta x. The middle term would be theta x, and the right hand side would be x. So 0 less than theta x less than x. And and as a consequence, what we have, e to the power of 0, that should be less than e to the power of theta x, and that should be less than e to the power of x. Okay, because e to the power of x is a monotone, strictly monotone function, so e to the power of left hand side should be less than e to the power of middlemost term, and that should be less than e to the power of the right hand side expression. And e to the power of x, over here x is a real number, therefore e to the power of x should be a finite number, and e to the power of 0 means that is equal to 1. Therefore what we have, we find that e to the power of theta x lies in between two finite numbers. The lowermost number is 1 and the uppermost number is e to the power of x. Got it? Now we multiply this inequality by x to the power of n by factorial of n. Okay, so now observe very carefully. You see over here, at first we are multiplying this inequality by a positive number x, but if x becomes if x is a negative number, then in place of this less than inequality we shall have greater than inequality. Okay, but after this one, in this term again we are multiplying by x to the power of n. Therefore if x is negative quantity, then multiplication of this inequality, which is a greater than inequality, then multiplication of this inequality by x to the power of n, that would again be a negative number if x is a negative quantity. So this x to the power of n would be a negative number if x is a negative quantity. Then we multiply this inequality by this negative number x to the power of n by factorial of n. Then it would lead again to this less than inequality. So greater than inequality will be converted into ultimately a less than inequality. So in any cases, if x is greater than 0 or less than 0, in any case we will have this kind of inequality. Got it? And that is written in this way: an less than rn and rn is less than bn, where an is equal to x to the power of n by factorial of n, and bn is equal to this x to the power of n by factorial of n into e to the power of x. That is actually is equal to an multiplied by e to the power of x. Got it? So in any case, whether x is greater than 0 or less than 0, we shall ultimately have this kind of inequality, an less than rn, and that is less than bn. Okay. Therefore, we can continue our discussion for any positive or negative value of x. Okay. Now, over here, what is an? An is equal to x to the power of n by factorial of n. Therefore, an plus 1 by an, its modulus, should look like this. Over here, this factorial of n plus 1, if it is cancelled with this factorial of n, then we shall have simply the factor n plus 1 in the denominator, and in the numerator we shall have this x only, a single x. And as because x is a real number, so if real number is always a finite number, we know this result that x is a real number, therefore it's always a finite number. And in that case, finite number divided by a quantity n plus 1 and with the limit n tending to infinity, then ultimately we would get this result as equal to 0. Got it? Therefore, we can say that this quantity is less than 1. And as because this is less than 1, so we can now conclude that this an tends to 0, and as a result this bn is equal to an into e to the power of x. X is a finite number, so e to the power of x is a finite quantity. This second factor is a finite quantity over here. Therefore, we can say that as an tends to 0, therefore bn should also tend to 0. Got it? Therefore, in any case, what we got the result that an tends to 0, bn tends to 0, and therefore the intermediate term, by sandwich theorem we can say that this intermediate quantity Rn in between an and bn, this intermediate quantity Rn should tend to 0. Therefore, we have this result that this intermediate quantity Rn tends to 0 as n tends to infinity. Got it? And I have just written that similarly, if x is less than 0, we have all these results. Over here, you see, it should be less than inequality. Sorry, I made this mistake. It should be less than inequality. This kind of inequality. Anyway, so in both of these two cases, we can prove that Rn tends to 0 as n tends to infinity. Okay, so Rn tends to 0 as n tends to infinity. That means all the requirement for application of Maclaurin's infinite series or the Taylor's infinite series in Maclaurin's form, all the requirements are satisfied. Therefore, just what we can do, we can just expand it. Fx is equal to f of 0 plus x into f dash 0 plus x square by factorial of 2 into f double dash 0 in Maclaurin's form, dot 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 etc. and so on. And you see that f of 0, we have the result that what is fx? F of x is equal to e to the power of x. So f of x is equal to e to the power of x, and therefore we can say that f of 0, that is equal to 1 over here. And what is fn? Fnx is also e to the power of x. Therefore, this f dash 0, the first derivative, n is equal to 1. For the second derivative, n is equal to 2. All these quantities should be is equal to 0. Got it? Therefore, we can say that all these quantity not equal to 0. Sorry, all these quantities are equal to 1. This fn at the point 0, that should be is equal to e to the power of 0. So e to the power of 0 means is equal to 1. Okay, so all these quantities, this f dash, f double dash, f triple dash, all these quantities become is equal to 0. Not 0, sorry, again I'm making mistake. All these quantities become is equal to 1. So what we have the result that this f dash 0 is equal to 1, so x into 1, that is actually is equal to x. Similarly, x square by factorial of 2 is equal multiplied by 1, that is equal to x square by factorial of 2. Similarly, x cube by factorial of 3 multiplied by 1, that is actually is equal to x cube by factorial of 3. And in this way we get the total expansion that you generally got in probably in your class 11 or in class 12 level. So we ultimately get this infinite series expansion, and this infinite series expansion is written in shortcut as a summation in this fashion, that summation n is equal to 0 to infinity x to the power of n by factorial of n. Now is it clear to you? ব্যাপারটা পরিষ্কার হলো কেন এরকম ভাবে এক্সপানশনটা পাচ্ছি? কোনো কোশ্চেন? এনিবডি? ডাজ এনিবডি হ্যাভ এনি কোশ্চেন?
No, sir.
So hopefully it is clear
No,
to you
sir.
all. Okay, thank you. So now let's continue the technique to another function that is equal to the function sin x. So we are considering this function fx is equal to sin x. Same kind of question is there. I am solving this question for you and keeping the same kind of expansion for the function cos x as a homework for you. Okay. So we know that fx is equal to sin x. If fx is equal to sin x, then any derivative can be represented in this fashion: sin of x plus n into pi by 2 for all x belonging to R. Over here it is again is not, we do not have any restriction on x, so these results are true for all values of x. And the result is also true for all n. That means the nth derivative is equal to sin of x plus n into pi by 2. This nth derivative exists and is continuous for all value of n, for all positive integer n. And what is Lagrange's form of remainder over here? Lagrange's form of remainder is equal to this kind of expression fn theta x. So just by putting x is equal to theta x, we got this result. And again we know that sine of any quantity, sine of anything, theta x plus n into pi by 2, sine of any quantity, these quantities always lie in between -1 and +1. So sine of any quantity always lie in between -1 and +1, and therefore if we multiply this inequality by x to the power of n by factorial of n, then we get this type of result. Okay. And ultimately we get the result that this left hand side and right hand side are very similar, except this symbol, except this negative sign. So we can write this left hand side as equal to minus an, and the right hand side is equal to an. An is equal to x to the power of n by factorial of n, and this middlemost term can be now written as Rn. And similar to the previous example, we can now show that this limit n tending to infinity an plus 1 by factor by an plus 1 by an its modulus, that is less than that is equal to 0, that is actually less than 1, and therefore we can now conclude that this an tends to 0 as n tends to infinity, and so by sandwich theorem we can say Rn tends to 0 as n tends to infinity, and this is valid for all value of x belonging to the set of real numbers R. And therefore we can again apply the Maclaud's infinite series expansion, and this is the Maclaud's infinite series expansion, and f of 0 would be is equal to 0 because we have f of 0 is equal to let me write the expression of f of x. F of x is equal to sin x. F of x is equal to sin x. So f of 0, that should be is equal to sine of x. Okay, so f of 0 is equal to 0. And what is fn x? Better writing in this way. Let me split the screen. Hopefully this would be comfortable for you. What is nth derivative? The nth derivative is if nx is equal to sine of x plus n into pi by 2. Therefore, if we put n x is equal to 0 and n is equal to 1, you will get the expression of f dash 0. So just by putting n is equal to 1 and x is equal to 0, then this would be sine of pi by 2. So we get the result that sine of pi by 2 is equal to f dash 0. Okay. Similarly, if we put n is equal to 2 and x is equal to 0, we will get the expression of f double dash 0. So we get it as sine of 2 into pi by 2. Similarly, the next one would be sine of 3 into pi by 2 and so on. But now sine of pi by 2 sine of pi by 2 becomes is equal to 1. So first term is 0, second term gives us x into 1. So it would be simply x. Okay. The next term is sine of pi. We know sine of pi is equal to 0. Therefore, no x square term is there. The next immediate term is x cubed by factorial of 3 into sine of 3 pi by 2. Sine of 3 pi by 2 is equal to minus 1. So we get this minus symbol over here along with x cubed by factorial of 3. Okay. Similarly, if we continue, ultimately you will get x to the power of 5 by factorial of 5 minus x to the power of 7 by factorial of 7 and so on. So this expression can be now written as this kind of summation, and that is actually the infinite series expansion of the function sine x, and this is true for all value of x. No restriction is there for this infinite series expansion on the value of x. Got it? So this is the expansion of sine x that we actually consider in different problems of mathematics, and probably you got this kind of result from some other perspective in your lower classes, but this can also be deduced for all value of x in this fashion by the help of Maclaurin's infinite series. Okay. And I'm keeping this expansion of cos of x. Exactly similar computation would be there. I am keeping the expansion of cos of x for your homework. Got it? I am leaving this one as an exercise for. Now let's discuss the infinite series expansion of this function log of 1 plus x. Got it? Where is it? Yeah, this is the power series expansion of no, not this one, log of 1 plus x. Yeah, this one, log of 1 plus x. Where is it? This one, the power series expansion of log of 1 plus x. So the power series expansion of log of 1 plus x, over here you see log of 1 plus x is defined only when x is greater than minus 1, and thereby we impose a restriction on the values of x. Got it? Okay. So apparently we are considering this function fx is equal to x belonging to R, but ultimately when we closely observe this log of 1 plus x, we should say that x should be defined for those points in the set of real numbers R at which log of 1 plus x is defined. That means x should be greater than minus 1. If x becomes less than minus 1 or equal to minus 1, in that case this log of 1 plus x, this expression would have some imaginary value. You might have got this kind of expansion or expression in case of complex numbers. Okay. So if x becomes a complex number, then the log of 1 plus x, this expansion would be true for all complex numbers. No problem would be there. However, if you consider the real analysis, and if you want any real value of the function fx, then this x must be a real number, and that real number must be greater than -1. Okay, so what we observe is that this fnx must exist. This is a standard formula of nth derivative of log of 1 plus x. I am applying the standard formula. Okay, and this fnx exists only for x greater than -1. Okay, and this should be true for all positive integer n. So what we observe that the nth derivative fnx exists for x greater than -1 and for all positive integer n. Therefore, it remains to show that the remainder Rn converges to 0 as n tends to infinity. And we discuss this case in the following, this situation in the following two cases. In the first case, we considered the fact that 0 less than x less than or is equal to 1, because the expansion we are going to get would not be a convergent expansion when x is greater than 1. So we consider the interval, the semi-open interval. Over here the interval should look like this: the semi-open interval -1, comma 1 plus 1. Okay, and in the first case we are considering this kind of semi-open interval: 0 less than x less than is equal to 1. Okay, so now in this first case we are considering this result, and over here you see for x is equal to 0 we already have the expansion of fn 0. So we shall always consider the cases when x is greater than 0 and when x is less than 0. In the first case we consider x greater than 0. Okay, and the Lagrange's form of remainder is considered. We have the expression of fn x over here. Just by putting x is equal to theta x in this expression, we get the expression of fn theta x. And now look at this expression little carefully. This factorial of n minus 1 will get cancelled with the factorial of n, leaving only one factor as small n in the denominator. And this -1 whole to the power of n minus 1 is kept as it is not changed at all. Now this x to the power of n divided by 1 plus theta x whole to the power of n, these two quantities are combined together and they form this result, that x by 1 plus theta x whole to the power of n. And we are going to show that this quantity is a finite quantity, particularly this is tending to 0 as n tends to infinity. We are going to show that this second factor is tending to 0 as n tends to infinity. How to prove this result? We have these two inequalities: 0 less than x less than is equal to 1 and 0 less than theta less than is equal to 1. We have these two quantities. So if this inequality, this first inequality is multiplied by theta is a positive quantity, so we have 0 less than theta x less than or is equal to theta. And we then add 1 on left hand side and on the middle term. Okay, so we already, in that case, we have the result that 1 less than 1 plus theta x. Got it? And now both of these two quantities are positive quantity, therefore if we take the inverse, this greater than symbol will be converted into a less than inequality. And of course, as because 1 and 1 plus theta x are positive, therefore this inverse quantity should always be greater than 0. Inverse of a positive quantity is also a positive quantity, it cannot be a negative quantity. Hmm. Now we multiply this expression by x. Then we have x greater than x by 1 plus theta x, that is greater than 0. And that is rewritten again in the form of less than inequality. Over here 0 was in the right hand side, so we are now writing 0 on the left. So this 0 should be less than is equal to this middlemost term x by 1 plus theta x, and that is less than is equal to the left hand side. So left hand side is equal to x, and we already have the result that x is less than or is equal to 1. So we can say that x is less than is equal to 1. So what have we have the result that x by 1 plus theta x, this quantity x by 1 plus theta x, this is positive quantity and less than 1, strictly less than 1, and therefore this whole to the power of n, that is also a quantity which is a positive quantity and strictly less than 1, and of course this quantity would ultimately tend to 0 as n tends to infinity. Although we don't need to prove all these results that this quantity is tending to 0, just we need to ensure that this quantity is a finite quantity. Why? Because over here we already have a number n over here. Okay, we already have a number n. So if n tends to infinity, then the modulus of Rn or simply Rn would ultimately tend to 0. Just we wanted to ensure that this quantity is not tending to infinity. Just we need to ensure that this quantity is a finite quantity. So a finite quantity multiplied by 1 by n, that would ultimately lead us to conclude that Rn tending to 0. Got it? So if we consider the modulus on both sides, we can say a modulus of minus 1 whole to the power of n is equal to 1, and that would remain that modulus of this kind of expression, that is always obviously less than 1. So ultimately we can say that modulus of Rn, this modulus of Rn is less than 1 by n. Got it? And this 1 by n tends to 0 as n tends to infinity. Therefore we can conclude that Rn tends to 0 as n tends to infinity, in the case when x is positive number and less than or is equal to 1. Now we consider the second part when x is negative number and greater than minus 1. And in this case, if we consider the Lagrange's form of remainder, then this Lagrange's form remainder would be a bit difficult for our computational manipulations. And that's why we consider Cauchy's form of remainder in this manipulation, because by Lagrange's form of remainder it would not be easy for us to show that Rn tends to 0. Computationally it would be difficult. And over here we are considering Cauchy's form of remainder. So the Cauchy's form of remainder ultimately gives us in this fashion. And what is the benefit? The benefit is that this factorial of n will get this factorial of n minus 1 will get cancelled with the new factorial of n minus 1 in the numerator. Minus 1 whole to the power of n minus 1, keep it unchanged. X to the power of n is there, so I'm keeping this x to the power of n, and over here 1 minus theta to the power of n minus 1, that is adjusted with 1 plus theta x, that is combined with 1 plus theta x to the power of n minus 1, keeping one extra factor 1 plus theta x separate. So I am keeping this extra factor 1 by 1 plus theta x separate, and that would not arise any problem, because ultimately this factor would be a finite quantity. So our target is to show that this expansion is tending to 0 as n tends to infinity, and the remaining quantities, that means this x to the power of n, that would be a finite quantity, because x is a finite real number, and these expressions etc., these are all finite quantities. So just we need to show that ultimately that Rn tends to 0. Now how to show this result? We need to construct this expression 1 minus theta divided by 1 plus theta x. Okay, how to show this result? Over here, firstly we have the result that -1 less than x less than 1 and 0 less than theta less than 1. So directly we can say that modulus of x is less than 1, and this implies that this modulus of x to the power of n tends to 0 as n tends to infinity. So one factor is tending to 0. Just we need to ensure that the other factors are finite, or they may tend to 0. It doesn't matter. What we have? We are multiplying this first inequality by a positive quantity theta. Then this less than inequality will keep this one as a less than inequality. So we have the result that minus theta less than theta x less than 0. It is actually some manipulation of inequalities. That's all. It might be a bit little boring, but it is nothing but the manipulation of some inequalities. So you need some practice in this part. And without practice, even if you tell me to appear the examination, I might be a failure guy for passing the examination on these kind of problems. So it is my advice to you all that you keep practice of this particular few problems, because out of this part, the infinite series part, only these 4 or 5 problems are there. No more problems are selected in exam other than these problems. Okay, that is the advantage, because the teachers also know that if we give you any arbitrary problem and show you to show the convergence, then it would not be possible for anybody else, even for an expert, to perform in exam at least. Anyway, so let's continue over here. So from this result, what we are doing over here, we are firstly considering, forget about this inequality. What we are doing, we are adding 1 throughout this inequality. Then we shall have what we shall have. We shall have 1 minus theta on the left hand side, and that is less than 1 plus theta x in the middlemost term, and that is less than 1. Okay. Now we are given that theta is less than 1, and therefore we can now have get this restriction that 1 minus theta is a positive quantity. So what we have, we ultimately have this type of result, that 0 less than 1 minus theta, that is less than 1 plus theta x, that is less than 1. And now 1 plus theta x is a positive quantity. So if we divide the entire inequality by 1 plus theta x, forget about this inequality, now we divide this total expression by 1 plus theta x. Then what we have on the right hand side, we shall have 1, on the left hand side we shall have 0, and on the middlemost part term we had 1 minus theta divided by 1 plus theta x. We are making this expression because just looking at this term, we had this kind of expression. That's why we wanted to generate the same kind of expression, and the upper bound and lower bounds. Over here the upper bound is equal to 1 and the lower bound is equal to 0, and therefore you can say that over here as well, this quantity to the power of n minus 1, that would ultimately tend to 0 as n tends to infinity. Got it? So now what we have, we have this expression that this is tending to 0, we have the result that this is tending to 0, and just we need to ensure that this quantity is a finite quantity. This last factor is a finite quantity. So that is the final computation over here. We already have this result, 1 minus theta less than 1 plus theta x, that is less than 1. And now if we consider the modulus of this expression, is greater than modulus of this expression, and this is a positive quantity. So we can remove the modulus symbol over here. We can write modulus of 1 minus theta is nothing but is equal to 1 minus theta, and therefore if we consider the inverse, then this greater than inequality will be converted into less than inequality, and therefore we have the result that 1 by 1 plus theta x, the last factor in the expression of Rn, that is a bounded quantity, 1 by 1 plus theta, sorry, 1 by 1 minus theta. Theta is a finite number, therefore it's a bounded quantity. Got it? So what we have, we can now say that this Rn, that is minus 1 whole to the power of n, its modulus would be equal to 1. So we have Rn, modulus of Rn is equal to this expression multiplied by this kind of modulus multiplied by this kind of modulus, and we already proved that the modulus of this last term, is less than 1 by 1 minus theta. So we can say that is less than is equal to first term into last term multiplied by 1 by 1 minus theta, and both of these first two factors, this factor and these factors, are tending to 0 as n tends to infinity. Therefore we can say that Rn tends to 0 as n tends to infinity. Got it? So finally, we combine both of these two cases, case number 1 and case number 2, and we find that this result, this Rn tends to 0 as n tends to infinity. And we did not consider x is equal to 0, because in the first case we considered this inequality that x is strictly less than 0, and in the second case we considered x is strictly less than 0, and in the first case we considered x is strictly greater than 0. So we actually did not consider x is equal to 0. Got it? And therefore we impose the restriction that x is not equal to 0. So with x not equal to 0, we have this type of inequalities, that f of x, we have this type of expansion, that f of x is equal to f of 0 plus x into f dash 0 and all, etc, etc, etc. And we already got the expressions of fn 0. So just put n is equal to 1, you will get is equal to 1. Similarly, if you put n is equal to 2, you will get this result as equal to minus 1 factorial. If you put n is equal to 3, you will get f triple dash 0 is equal to plus 2 factorial, and so on. So now by further computation we get this type of result, and that can be written in this way, that log of 1 plus x can be written in this kind of summation formula. And you see over here, if we put x is equal to 0, we know that log of 1 plus 0, that is actually log of 1, isn't it? And log of 1 is equal to 1. Log of 1 is equal to 0. So left hand side is equal to 0. And if we put x is equal to 0 over here, the right hand side is also is equal to 0. So we can say that both of these left hand side and right hand side both become is equal to 0 at x is equal to 0. Therefore we can say that this expansion is also valid at x is equal to 0. And so we can say that the expansion is valid throughout the interval minus 1 less than x less than or is equal to 1. Got it? Therefore this is the restriction that we need to impose on log of 1 plus x. Okay, and one more expansion is there. I am currently not going to discuss this expansion, because firstly it is already written over here, different several cases arises, and this expansion is a bit rigorous, computationally a little bit boring and difficult. But it says that it says that 1 plus x to the power of m, this expression, we need to find the power series expansion of 1 plus x to the power of m for all real number m. We know that if m is a positive number, then we can expand this expression in the using the binomial law. So, but if m is any real number, maybe a fraction, maybe negative number, maybe rational number, maybe irrational number, in that case also we can expand this expression fx in this expression of 1 plus x whole to the power of n, and all the calculations are shown over here. I am keep leaving this calculation for you. I am not going to the discussion, because the discussion is getting very boring over here. However, my advice would be for you to, if you get this question in your exam, please try to avoid this question, because although the computationally it may become difficult not only for the computational point of view, it would be a very time consuming affair in exam at least. Hmm. So I'm leaving this one for you, so that you can go through this portion, and if you have any further query now, you can ask me. But before that, let me thank you for your patience and having me with in this class. And if you have any question right now, you can ask me.